Okay, for this video, I'll be going through DC circuit tutorial 1. Okay, so the first question is to calculate the effective resistance. So sometimes you call it RE or REFF. Okay, or sometimes you can use R total to denote that is a total resistance. Okay, so 1A, you see that the three resistors are connected in one line, one after another. So basically, they are connected in series. So you can use the series formula R1 plus R2, and in this case, because we have the third resistor, we can add a R3. Okay, that means as long as you have resistors in series, no matter how many, you can even do until Rn, which is the n is the number of resistors. So you add up, it becomes 4,700 ohms. Okay, so for B is a little bit more complicated because we have this 3 ohm, and as the current flows towards here, you will see that the current actually splits into two paths. Okay, split, again, it doesn't mean that it is equal strength of the current. Okay, so basically when it splits, when the current splits, it means the two resistors, there are two paths, two resistors are connected in parallel. Okay, so what we can do is we can work out what is the effective resistance of these two resistors that are in parallel. So the effective resistance formula for parallel resistors is 1 REFF plus 1 over R1 plus 1 over R2. Okay, so after you get your answer, so I'm going to use 1 over 5 plus 1 over 4. Okay, you are going to get 9 over 20, right? So this is not the effective resistance because now it is 1 over REFF. So the REFF is now actually, you need to flip, becomes 20 over 9. Okay, so it's 20 over 9. So if I were to redraw this circuit, because I didn't do anything to the 3 ohm, then I have my 20 over 9, right? So after redrawing, you find that actually the parallel resistors becomes 20 over 9 ohm. By right, I should leave it in 3SF. Okay, you'll find that these two resistors, which is the 3 ohm plus the REFF, is actually now in series, right? So then you can add them up together and you should get 5.2. Okay, part C. So we can again have the current flow to this place, and then it splits up into two path. That means this path, the top path, and the bottom path, they are in parallel. Okay, but what's different here is that for the top path, I can actually add up these two resistors first. So if I add up and I find that they are actually in series for the top path, we get 3 ohm, right? So I'm redrawing. And for the bottom path, I have my 5 ohm because I never do anything to it. And then if I apply the parallel resistors formula, I will get about 1.9 ohm. So this is in 2SF. Okay, D, current against flow to this place. You find that there's a top, middle, and a bottom path. Okay, so these three paths means these three resistors are in parallel. So I can use my parallel resistors formula, 1 over 8. And in this case, because there are three resistors in parallel, so I can do this 1 over 8 plus 1 over 4 plus 1 over 2. And remember, after you get a certain value, it is not the effective resistance yet. You need to still flip it. Okay, so after you do it, you should get about 1.1 ohm. Okay, now question 2, they are asking us to rank the brightness of lamp in ascending order. Okay, so the brightness of the lamp each depends on the amount of current flowing through it. So you have already covered practical electricity, whereby the power of the light bulb, it is the energy that's being transferred to the light bulb goes by the formula of I squared times R. Okay, so because the resistance, if we take it that it doesn't change, then the power dissipation will then be based on the amount of current, right? So if we want to rank it in brightness, we will rank it in the power. Okay, but we don't need to calculate that. We just need to see which resistors has the most current, and therefore it will be the brightest. So the current flows out. That means L1 will get the full current. Okay, because that is the most current that comes out from the battery. The current flows to this node, and the current will split up because now there are two paths. So it will flow through L2 and L3. And since L2 and L3, they are the same light bulb, same kind of light bulb, identical. Therefore, the current will split up equally. That is if the resistance of each path is the same. That means the brightness of L2 will be equal to L3, but because it is half of the current that is from the battery, therefore it will not be as bright. In fact, it is half the brightness. No, it is not half the brightness. It is half of the current. So example, if the current here is 2 ampere, it will then split up into 1 ampere and 1 ampere. And once they reach this place, they will combine to form 2 ampere. Therefore, L4 will have the same current as L1. Okay, so this is how I present the answer. L2 equals to L3, right? So they are the least bright, comma, followed by L1 equals to L4. They are the brightest. Okay, in that case, L1 and L5, you should know that they are the brightest. L1 equals to L5. Now, when the current comes here, we see that there are actually two paths to get to this node here. One path, the second path. And the first path, which is the one that passes through L3, it only passes through one resistor. For the second path, this one, it passes through L2 followed by L4. Therefore, this path actually has more resistance. If it has more resistance, right, that means there will be lesser current flowing through compared to the current that flows through L3. Therefore, L2 equals to L4 because they are both in series in this path, right? So they are both in series. So the current will actually be lesser than L3, and the one that has the most current is L1 and L5. Okay, so by now you should know that L1 and L6, they are the brightest. Now the current flows here. There are two paths. Okay, so the one on the left passes through L2 and L3. The one on the right passes through L4 and L5. Therefore, L2 equals to L3 equals to L4 equals to L5. Okay, this looks complicated, but if we follow the flow of the current, it comes over here. It splits up equally because L1 and L2, they are equal resistance, so they have equal current, same current. So by the time they come back and they combine, they should have the same current as before. And again, come to this node, there are two paths, so L3 is equals to L4. The current through L3 equals to L4, and all will have the same brightness. Okay, again, this looks complicated, but current flows here, it will split up. It will split up, one path will go through L2, the other half will go through L1. They meet up over here to become the main current, I. Okay, and again, they will split up. So they all will have the same brightness. Okay, this part is talking about short circuit. So just now we actually did a few parallel resistors. Okay, so if let's say I have this light bulb, which is let's say 100 ohm, and I have a resistor 1 ohm that is connected in parallel. So even though 1 ohm has lesser resistance, I will have more current flowing through it, and the 100 ohm light bulb has more resistance, I will have lesser current flowing through it, but there will still be current flowing through the 100 ohm. Okay, so this is different from the short circuit. For short circuit, if I were to connect a wire, and this wire actually has no resistance, we take it that it has negligible resistance and it doesn't have any resistors attached to it. This forms a short circuit whereby all the current will flow through it, all the current, right? Because this path actually has no resistance. So it is serving as a bypass. Therefore, the lamp will not light up. Okay. Okay, so now we can apply all this, finding effective resistance, analyzing how the current flow, into our electric circuit. Okay, so it shows a 12-volt battery. Okay, I have a 6 ohm resistor, 3 ohm resistor. I have a switch which is open. I have ammeter here. 2 ohm and 4 ohm is connected across PQ. So they want us to calculate the reading of the ammeter when switch S is open. So if switch S is open, that means any current that flows in this path will not be able to flow through because there is an open circuit. Okay, so I can actually withdraw and I ignore the top path completely because it is an open circuit. So that will make the effective resistance to be 6 ohm because now there is only one path, so I can add them up, it become series. Okay, so I can actually withdraw again to make it into 6 ohm and then 12 volts. Okay, now that I have my V and my R, I can actually find the current, which is then 2 ampere. Now, a common mistake is that students will just take 12 volts divided by 2, okay, the first resistor to find the current, but this is not correct. So always try to find the effective resistance. Now, switch S is closed. Calculate the combined resistance of the 3 ohm and 6 ohm in parallel. So I can just draw my 6 ohm and my 3 ohm, and I want to find their effective resistance. So 1 over REFF equals to 1 over 6 plus 1 over 3. Okay, so 1 over REFF is equals to 1 over 2, right? So REFF, remember to flip, will be 2 ohm. So this flipping part is actually the most common mistake that I always get, that I always see in the student script. Okay, so combined resistance is 2 ohm. So they want us to calculate the current through the battery or the current that flows out from the battery. So the purpose of this is to help, part B is to help us in part C. So now let me redraw the circuit with the 2 parallel resistors, okay, replaced by the 2 ohm resistor. Okay, so this is switch S. This is 2 ohm. Okay, and I can actually combine these two because I have the 6 ohm, right? So they want the current that comes out from the battery. So the current comes out, it splits into 2 paths, which means this 2 ohm and this 6 ohm is in parallel. So I can combine them using the effective resistance formula for parallel resistors. So I should get 1.5 ohm. Okay, so now that I have my effective resistance, I have only one resistance in the circuit, I can actually calculate the current. So 12 divided by 1.5 ohm, I get 8 ampere. So this is the answer. Okay, now what's the current through the 4 ohm? Now where's the 4 ohm? The 4 ohm is actually located here. Okay, so if I can find the current, through this 6 ohm, which is actually a 2 ohm and 4 ohm in parallel, and current in series is actually the same, right? So as long as I can find this current through this 6 ohm, it is equal to the current that flows through the 4 ohm and 2 ohm, which they are in series, right? The 2 ohm and 4 ohm, they are in series. So this is 12 volts. Now, I noticed that these two resistors are in parallel. Okay, they are parallel. So I can actually apply in parallel, voltage is the same. Okay, that means across this 2 ohm I have 12 volts. Across this 6 ohm I also have 12 volts. So let us calculate the current through this 6 ohm, which is in fact a combination of my 2 ohm and 4 ohm. So I should get 2 ampere, isn't it? Okay, therefore the answer is 2 ampere, right? But I need to just maybe check. Okay, so I can check that for what is the current that flows through the top 2 ohm resistor. So I have the V, because that's the voltage or potential difference across the 2 ohm. I divided by 2, I will get 6 ampere. Okay, so remember just now we ask you to calculate the current through the battery, right? So this 6 ampere and this 2 ampere, they actually add up to become 8 ampere. So that means my calculation is correct. That's how I can check my answer in exam. Okay. Okay, now part E, this one I explain any change to the current through the 4 ohm resistor when a 6 ohm resistor is now connected across the points P and Q. For this, I got a lot of different answers, a lot of wrong answers. Okay, maybe I'll redraw the circuit again. Okay, so this is my 2 ohm and this is my 4 ohm and the 4 ohm resistor. But I just keep my 6 ohm here. Now they are proposing that a 6 ohm resistor is now connected across the points PQ. Where's PQ? PQ is actually, points PQ is actually here. Alright. So what the question meant is that now I have another 6 ohm that is connected across PQ. This 6 ohm is connected across PQ. And it doesn't mean that the 6 ohm is connected in series to it. Okay, so this is incorrect. This is not what the question wants. So remember, in parallel, the voltage is the same. That means even though I have a 6 ohm that is connected across PQ in parallel, it doesn't affect the potential difference of voltage across the 6 ohm. So the current will remain the same. And this is what the answer is saying. So the current will remain the same because the potential difference across the 4 ohm and 2 ohm resistors, which is our 6 ohm combined, remain the same when a new 6 ohm resistor is connected across PQ in parallel. Okay? So that's why the current remains the same. Okay, question 4. We see that we have a EMF, a battery of EMF 4.5 volts. Current flows. Comes to this point, it will split. Okay, how the current splits, I don't know. So we can find out now. Firstly, they are asking what's the potential at A. The potential difference across this battery is 4.5 volts. So the potential here is 4.5 volts. The potential here is 0 volts. Now, what is the rationale? Because if I want a potential difference of 4.5, the positive terminal must be at a potential of 4.5 and the negative terminal must be at a potential of 0, because anything minus 0 is anything. So we have solved A and B. And what's the potential difference between A and B? Now the potential over here is 0 volts, potential here is 0 volts because it doesn't have any resistors along this path. Similarly, over here is 4.5 volts. Over here is 4.5 volts because along this path there isn't any resistor, so there is no change in potential. So the potential difference between A and B is 4.5 volts. Now they're asking what is the total current drawn from the battery. So I need to resolve this. So actually I can redraw the circuit as such. 2 ohm, 7 ohm, okay, and 4 ohm, 5 ohm. Okay, I just stretch the wires a little bit and this thing looks more familiar to you all, right? So this is 4.5 volts. Now what is the effective resistance over here? Because they are connected in series, so it becomes a 9 ohm. Okay, and over here again they are connected in series, so also 9 ohm. Okay, so what is the effective resistance of 9 ohm and 9 ohm in parallel? Will be 4.5 ohm. So let me redraw the circuit. Okay, 4.5 ohm. X and Y disappear, but it's okay. So they are asking for the current that flows out from the battery. So 4.5 divided by 4.5, V equals IR, I get 1 ampere. Okay, now what is the potential difference between X and Y? So because we have finished using this, we use this to find our 1 ampere. We can substitute our 1 ampere back here. Okay, now these two resistors over here, okay, gives a total of 9 ohm, and here also gives a total of 9 ohm. That means they are these two paths has the same resistance. Okay, which means the current will split equally to be 0.5 ampere and 0.5 ampere. Over here, I say they split equally because both paths have the same resistance. On the other hand, we can also take it that here is 4.5 volts, the potential. Here is 0 volts. So across this 2 ohm and 7 ohm, the potential difference is 4.5 volts, right? In parallel, the potential difference is the same. That means over here, I also have a potential difference of 4.5. And 4.5 volt divided by 9, which is my V equals to IR, my current will be 0.5. So this is valid. Apply this again, V equals IR, 4.5 volt divided by resistance, my current will be 0.5. So again, this is valid. Okay. Okay, so it's a little bit messy. Let me clear it up. Now we go back to the actual circuit that shows the X and Y. We now know that the current that comes out is 1 ampere. Okay, and over here the current is 0.5 ampere, and here is also 0.5 ampere. They want us to find the potential difference between X and Y. So we need to find the potential of X and potential at Y lah, maybe not of. Okay, potential at X and potential at Y. Okay, so at this point here, the potential is 4.5, right? As the current flows through, the potential difference across this 2 ohm will be V equals to IR. The V is the potential difference. I is the current 0.5. The resistance is 2. So the potential difference is 1 volts. So in order to get a potential difference of 1 volt, here is 4.5. Here at Y must be 3.5, right? Because 4.5 minus 3.5 will then give me a potential difference of 1 volts. So if we do the same for X, 3.5 volts for Y. If we do the same for X, we have 0.5 ampere flowing through this current of 4 ohm. So the potential difference will be 2 volts. The potential difference will be 2 volts, right? Because V equals IR, the current is 0.5 ampere, the resistance is 4, so I will have potential difference of 2 volts. Now, the potential here at A is 4.5, so in order to get a potential difference of 2 volts, X must be 4.5 minus 2 to be 2.5 volts. Okay, so we have found the potential at X and the potential at Y. So the potential difference between X and Y will be 3.5 minus 2.5 volts. Okay, so we'll get 1 volt. Now, can we check our answers? So since we say that at Y, the potential is 3.5 volts, right? And over here, the potential here is 0. So the potential difference across the 7 ohm will be 3.5 minus 0, which is 3.5 volts. So using V equals IR, this is my V, and this is my R, which is 7 ohm. My current that flows through the 7 ohm, it is, current is 3.5 divided by 7 equals to 0.5 ampere, which is what we had at the initial, right? Because the current from 1 ampere split into 2 equal paths, 2 paths of equal resistance, so it's 0.5. And 0.5 current, 0.5 current, 0.5 ampere, 0.5 ampere, right? So in series, the current is the same. Okay, question 5, 3 cells, each of EMF 2 volts, so total they will have a total EMF of 6 volts. They are connected in series, right? So ammeter and 2 voltmeter are used to measure the current and voltage. What's the current flowing through each resistors? So most of you can do this because the resistors are connected in series, and most of you have read these 2 volts each. So you should get 0.013 ampere. And because they are both connected in series, so the current is the same. Now what's the PD across? It is 2 and 4, and if you add them up, it should be equal to the EMF of 6 volts. So this is how you check, and this is how you draw. So we just expand this a bit. The positive is at the long side, the negative. Now ammeter, we should have negative, positive, negative connected to negative. Okay, positive is connected to positive. So for voltmeter, also the same thing. Voltmeter connected in parallel, negative to negative, positive connected to positive, minus plus. Okay. So a number of 8 ohm resistors are available. Draw diagrams to show how you connect a suitable number to give an effective resistance of 24 ohm. So we can just add 3 of them together. So 24 ohm. Okay, how do we get 18 ohm? Now, if I have these 4, so their effective resistance will be 1 over 8 plus 1 over 8 plus 1 over 8 plus 1 over 8. Okay. But there's this trick here. If I have 2 resistors in parallel and they are equal in magnitude, 2 resistors in parallel, if it's 8 ohm and 8 ohm, they are equal in resistance, right? I can just take the one of the resistance value and divide by 2 because I have 2 of them in parallel. So this will be 4 ohm. Okay, how about if I have 4 resistors that are in parallel and all of them having a resistance of 8 ohm? I will just take 8 ohm divided by the number of path, right? Because they are equal resistance, so I'll get 2 ohm. Okay, so therefore this is actually 2 ohm resistor. This is 8 ohm, this is 8 ohm, 8, 8, 2, right? I'll get 18 ohm.